So, is all of physics wrong? I know, it's a super bold question, right? But it actually gets to the very heart of how science works. See, the goal isn't always to be perfectly 100% right. It's more about building better and better maps of reality. So let's dive in and really explore this idea, the amazing power of a theory that's just good enough.
All right, to really get this, we got to jump in a time machine and go all the way back to 1896. This is the physicist Albert Michelson. And this quote, wow, it just perfectly captures the feeling of the time. The thinking was, hey, you know what? We've pretty much figured out physics. Seriously, they thought all the big foundational laws were set in stone, and all that was left was just, tidying up a few loose ends. It was this moment of absolute confidence, which, as we're about to see, was just completely off the mark.
And this is where it gets kind of wild. The irony here is just perfect. Check this out. On the left, you've got those small details that guys like Michelson thought were just minor annoyances. That first one, a weird little measurement of something called the luminous ether, well, that little thing led directly to Einstein's theory of relativity. And the second one, this pesky problem in electromagnetism, that basically blew the doors wide open for quantum mechanics. Think about that. The two absolute pillars of all modern physics, they literally came from the tiny cracks in the old theories.
So that brings up a really important question. Does this mean someone like Isaac Newton was just wrong? Well, no, not at all. Not even close. I mean, we still use his laws of motion and gravity to launch rockets to this day. A much better word is incomplete. And that's the key takeaway here. Science doesn't usually move forward by throwing old ideas in the trash. It moves forward by finding the edges, the limits of a theory, and then building a bigger, more complete theory that still includes the old one inside of it.
This whole idea has a name. It's called a range of validity. Think of it like this. Newtonian physics, over on the left, is the perfect map for our everyday world. You want to calculate the curve of a baseball? Perfect! You need to land a rover on an asteroid millions of miles away? Newton's got your back. But once you get to really extreme situations, like things moving close to the speed of light or the crushing gravity near a black hole, that map starts to fall apart. And that's when you need to pull out the newer, more detailed map, Einstein's general relativity. Okay, so this all leads to a huge question. Maybe the question for us today. If Newton's amazing theory was really just a fantastic approximation, then what about our current heavy hitters? What about general relativity and quantum mechanics? Are they the final answer, the ultimate truth? Or are they also just incredibly, incredibly good approximations? To even begin to answer that, we've got to take a deep breath and dive headfirst into the absolute weirdness of the quantum world.
Now, before we get into the problems, let's just be super clear about something. Quantum theory it's just unbelievably successful. I mean, it is without a doubt the most precise, most tested, most successful theory in the entire history of science, period. The predictions it makes are accurate to an insane number of decimal places. The device you're watching this on right now, your phone, your computer, it only works because of quantum mechanics. So there's no question that it works. The real head-scratcher is, what does it all mean?
All right, to find the crack in this perfect theory, we have to wrap our heads around one key, kind of mind-bending idea, superposition. So think about a normal light switch, right? It's either on or it's off. Simple. But a quantum particle, it's not like that. It can exist in this weird fuzzy state of being both on and off at the exact same time. It's in this weird combination of all its possible states right up until the moment you look at it or measure it.
And that leads us straight into something called the measurement problem. It's this deep fundamental paradox right at the core of quantum mechanics. So let's just walk through this. Step 1, you've got your particle, and it's in a superposition. Let's say it's both spin up and spin down at once. Step 2, you bring in a machine to measure it. Now here's the kicker. Step 3, according to the math of the theory, your measuring device should get tangled up in that superposition too. It should be in a state of reading both up and down at the same time. But step 4 is where reality crashes the party. That's just not what we see, ever. In the real world, we only get one single clear answer. The needle points to up or it points to down. It's never pointing to both.
The physicist J.S. Bell just nailed this whole dilemma with a brilliant quote. He said, "Either the wave function is not everything, or it is not right." And what that really boils down to is two possibilities. Option 1, the theory is incomplete. The quantum description of reality is missing something. There's some other stuff going on behind the scenes that we don't know about. Or option 2, the theory itself is wrong. The basic equations that tell us how things are supposed to evolve over time, they need to be fixed.
So Bell's dilemma basically gives us three main roads you can go down to try and solve this thing. First, you could say the theory is incomplete. Maybe there are hidden variables that are secretly determining the outcome. Second, you could say the rules of the game are wrong, that there's some real physical collapse that happens, which randomly picks one result. Or you could go down a third, really wild road and say the theory is perfectly fine as it is, which leads you to the many worlds idea. That's the one where every possible outcome actually happens just in its own separate parallel universe. And the craziest part? There's absolutely no agreement among physicists about which one of these is the right answer.
Okay, so with all this crazy uncertainty, how do we even think about this stuff? How do we make progress? Well, it really helps to come back to a simple but super powerful metaphor. The map is not the territory. That's it. Our scientific theories, they're just maps. They are amazing, detailed, human-made models of reality, but they are not reality itself.
And what that really means for science is profound. A theory doesn't have to be the final, ultimate truth of the universe to be unbelievably useful. A good map, a good enough approximation, can be so ridiculously precise that it lets us land a tiny spacecraft on a speeding asteroid millions and millions of miles from Earth. So finding where a map starts to get fuzzy, like where Newton's laws break down, that isn't a failure. That's a huge success. That's progress. Because it shows us exactly where we need to start drawing a new, better, more detailed map.
You know, physicists actually have a formal name for this whole good enough map philosophy. It's called an effective field theory. And the core idea is exactly what we've been talking about this whole time. It's the idea that you can have a theory that is insanely accurate for one specific part of the map, at certain energy levels or at certain scales, even while knowing full well that it doesn't describe the whole entire territory.
And that brings us right back to where we started, full circle. Because today, even our absolute best theory of gravity, Einstein's general relativity, is seen by most physicists as an effective field theory. It's this beautiful, stunningly accurate map for the low-energy world we live in, but we think it's just a map of a much deeper, much more mysterious territory, a final theory of quantum gravity that would finally unite the world of the very big with the world of the very small. It is, by far, the best map we have, but we are almost certain there's a better one out there, just waiting for us to discover it.
So where does that leave us? Well, with the ultimate question, really. As we keep drawing these better and better maps of reality, will we ever hit the bottom? Will we find that one, final, fundamental theory of everything? Or, as that old philosophical joke goes, is it just turtles all the way down? Just an endless stack of theories, one on top of the other, each one a better approximation than the last, but with no final ultimate ground floor? Honestly, we don't know. And that search, that not knowing, that's what makes science the most incredible adventure there is.